Discrete mathematics is the foundational framework to connect these fields of CS and mathematics, physics and engineering, criminal justice and law through rigorous structured logic and data manipulation. How and why? Well, in CS and mathematics, discrete mathematics uses logic proofs, induction, contradiction to verify algorithm correctness, and set theory to define data structures, database queries, and theoretical computer science. Meanwhile, physics and engineering in data science, this field employs matrices and linear algebra to model quantum mechanics, structural analysis, and physical simulations like oscillatory motion, circuits, computer hardware, and network analysis. Meanwhile, for criminal justice and law, discrete mathematics, could be helpful as it applies sets and logics to analyze evidence patterns, ballistic forensics, reconstruct crime scenes, and construct legal arguments or predictive policing models. So I am going to show you about discrete mathematics, mostly about logic and proofs for this video, and you can find this book with the IEE citation at Amazon. So notice this is at Amazon. This is the book that you would technically read to understand this concept about discrete mathematics and its applications by Professor Kenneth H. Rosen. So here it is. And it covers a lot about the mathematics applications about it, but for this chapter, I'm talking about logic and proofs, which is kind of correlated to a little bit on humanities side or liberal arts side or the English part of the concepts, not just a STEM, because STEM is related to mathematics, CS, physics, and engineering, and biology or chemistry, right? But on this side, we also include it because of the fact that sometimes logic and proofs can be useful in these fields. So to start off with logic and proofs, a proposition is a declarative statement that's either true or false. It is represented by the letter T and F for false. It can be clear phrases, statements, sentences, mathematical conditions, like coding, programming conditions as well. It cannot be questions, commands, and neither true or false. Another vocabulary to learn is a truth value is a truth or falsehood of a proposition. Some examples of propositions are Paris is in France. That is indeed true. The capital of France is in Paris. Meanwhile, Bogota is in Spain. That is false. Why? Because Bogota is the capital of the country Colombia. And the District of Columbia is not located in the country of the United States. That is false. It is actually located in the country of the United States. Washington, D.C. is in the USA. The District of Columbia or Washington, D.C. is the capital of the United States. That is true. If you were to Google this on Google, you would be able to see that the capital of the United States is indeed Washington, D.C. Some other proposition examples is like math, like 10 is less than 100. Is that true? Is the number 10 less than 100? That is true, so it would be represented with the letter T. Not a proposition examples by the definition. What major are you? Do your task. This proof is false. X and Y are divisible by 0, and Nikola Tesla, not a sentence or phrase condition. So you notice that these are questions, commands, neither true or false, and also depends on what X or Y represents. And the name of a person does not count because it's not a sentence or a phrase condition. For coding examples in different subjects, I will show you examples in Python because of the fact that it's easier to see and it's the newest language usually. And I do think that if you were to take this in computer science, you would see it more often in Java because that is usually the first class that you would take. Other than that, but I do think that it's better to understand Python in a sense because you don't have to worry about syntax and it's more straightforward. It's like an easier breakdown of a code than as if you were to write it in other complex codes. So for the coding examples in different subjects, the proposition can be used like in conditional statements like if-else statements, if X, do Y, Boolean logic, true or false decisions like if user ticket equals valid, then do this. Compound propositions using and or to combine conditions. For this example, I will show an example in computer science for cybersecurity. Conditional statements are used to monitor network traffic and detect malicious activity. Logical propositions. If traffic is coming from a blacklisted IP address, then block connection and log the event. So that is the if and the then, which is a conditional statement. For this pseudocode, you can see in Python that you can say if this is in blacklist, which is if the traffic is coming from a blacklist IP address, then with the semicolon, block connection, and then log the event, which is stating it saying intrusion attempt. And the else part is basically saying that if none of this are considered, like none of this is happening with the if and then you say allow connection. That means there is the traffic that's coming in is not a blacklisted IP address. It's an IP address that is allowed, that is approved from you. So thus, it is allowed a connection. The second example would be in criminal justice. Criminal justice can use these often, and this type of logic and proof to predict policing. Algorithms use data analysis or data analytics to determine where to deploy officers based on crime patterns. Logical proposition: if the crime rate in region A is above 75% and it is Friday, then increase patrols. So if the crime rate is higher, then you should increase or add more officers to patrol the area. So for this pseudocode, you can tell that if the crime rate is greater than 75% and the day is on Friday, then you should deploy more officers in zone A. And then else, if the crime rate is not really that high and it's on Friday, then you just perform the regular patrol. For physics, you most often will see this type of thing in simulation or gaming, like when you're building game dev or something, most usually. Other than that, you might see these conditions happening in circuits, especially in circuits when you're drawing the circuit diagrams, talking about the different currents going in and out. So that's how it is. A physics engine in a game uses conditionals to determine object interactions. Logical proposition: if the player's y position is less than or equal to the ground height, then set the velocity to 0 and stop falling. So right now the person is currently falling. It's the condition. It's running. Like let's say it is running. You're doing some game about something about bouncing balls or something like I don't know some bird game or something. Then you're going to say that if the player is less than or equal to the ground height, then set the velocity to 0 and stop falling. So it would set it to 0, and then the person is considered standing. For legal studies, you can see this often too in law and regulations, where the automated compliance systems use logical constraints to ensure transactions adhere to legal standards. You would technically see this in law, and the logical proposition will state if a money transferred is greater than 10,000, then flag for review under anti-money laundering AML laws. So it's just talking about if, detecting whether the person breached a policy to be considered as money laundering. So if the money transfer is greater than 10,000, then flag for review under anti-money laundering laws. So if this is greater than 10,000, flag for review, and then report to the Office of Finance. For finance, you can see this too. If you're going to build a finance application, usually with Python to analyze databases or data sciences, or even analyze the graphs, statistical graphs like stocks or something, crypto coins or something, you might often write this down or create your own programming if you want to. Trading software uses conditionals to execute orders automatically based on market conditions. If the stock price falls below 150 and the trading volume is high, then execute buy order. If this and high, execute buy. So now that we have an understanding about what a proposition is and what it is shown in different subjects and turned into code, we will see the math notations for different proposition types. Compound propositions uses connectives for propositions. In other words, connectives are used to create a compound propositions. So connectives are like symbols that we use in negation, conjunction, disjunction, exclusive or implication by conditional. And it's represented by this symbol here for these ones. And these are all to make a compound proposition using the words not, and, or inclusive, either, not both, inclusive, exclusive, if, then, if, and only if. And it's represented by this type of symbol notation of logic and proofs and represented the meaning of it. So let's go over it together. Negation would be represented by the negation symbol, and it means not. So representative with not P, and represented meaning is not P. Conjunction is a little hat triangle, which is called and. P and Q represented with this symbol. I'm not just going to state it like that. Disjunction would be kind of like a V look, which is a symbol, and it says or inclusive. So P or Q, which is inclusive or both. And exclusive or is this symbol with like a plus dot, kind of like what you see on batteries, kind of. Either, both, exclusive, and it's stated not both, exclusive. So either P or Q, but not both. Implication is started with an arrow like this, if and then. So that just states like the if and then kind of. So if P, then Q. If P, then Q. Biconditional means two arrows going back and forth. Symbol, if and only if. P, if, and only if Q. Yeah. So there we go. Each proposition has a propositional variable to represent these statements. Some letters like P, Q, R, S, etc., like not P or P, if P, then Q. Example, make a negation out of the statement, the White House is beautiful, which is a positive statement. To make a negation out of it, you put a negation out of it, which is not, so the White House is not beautiful. Or if you were to rewrite it in proper English, it would be the White House is ugly. So the compound proposition for that statement would be negative P, not P, and P stands for the White House is beautiful, which is a statement. To represent the compound propositions and the truth value of a compound proposition depends only on the value of its components, using F and T into the tables, filling in the tables with T and F. So below here is the truth tables that you're going to use to analyze in your mathematical exams about logic and proofs. So what we're going to state, or statements about propositions, you can represent it with P and Q. You will start with an empty box as a start. So this is what they're going to ask you at an exam, kind of, and they're going to give you the P and Q. They will not fill in the P and Q down here. You will have to fill in yourself. It will technically be every single box that's empty. And they're going to assume that you're going to do it properly, where you say P section would be TT, FF, Q would be TF, TF. Why? Because, you know, these are all the combinations of what P and Q is for these two variables only. The table will definitely be longer, and like both width and height, depending on how many variables you have. So in this case, there's two variables, only P and Q. You will usually just see only 4 rows to compare it. But if there's a third or fourth variable, it could be even longer than that, depending on how many combinations of truth and false. So when you start with empty boxes to start, it will show that. And then when you fill in on the truth tables based on the compound propositions, start with row 1, then down. So let's start. P is true. P is T, which is true. Q is T is true. So not P. So we're going to look at P here. And then we're going to look at the P area, which is true. And then you want the not P. So what is not P? It's false. And then when you want to determine P and Q, we're going to say P is true and Q is true. Thus, it is true for this too. For P or Q, which is inclusive, it would be, is P or Q true? Is either one of these true? And is it true? Yes, it is. Both of these are true, and one of them also is true. So thus, P or Q is true. For exclusive, it would be would be the either, but not both exclusive. So either P or Q is, true, but not both. So when you look at this statement, you can see that P is true, Q is true, and both of them are true. So thus this will be false, because in that statement for exclusive OR, there is no such thing as true, true, or false, false. So it can only be one or the other. So because it's not one or the other, then it's technically false. So this one will state P, if P, then Q. So if P, then Q is true. Is that statement true? Yes, it's true. So you write true. And then for this one is a biconditional, which is if and only if. P if and only if Q. So we do notice that P if is true and only if Q is true, which is true, and it's true here. You write T. And you would do the same for all the rows, and you compare it back and forth between this. So you compare here, compare here, you compare here, using the compound propositions and comparing them. So the answer will look like something like this. And then there are different types of it, which is tautology. Tautology, which is a proposition, is a tautology if a truth value is T for any assignment of truth values to its components. Another way to say a shorter way is a statement that's always true. Contradiction is a proposition if its truth value for F and any assignment of truth values to its components. Shorter version is a statement that is always F. Contingency is a proposition that's either a tautology nor a contradiction is a contingency. A statement either true or false. Yeah. So what you would start is empty, and then you'll make the basis of the combination true, true, false, false. And then you'll fill in the table. Negative P or not P, P or not P, and then P and not P. And then you'll fill in the table. So in this table, it's shown as it's like filled in with truth or false. And then you can see in the rows here, you can tell this is tautology because it's all like this. True, 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 always false. No, always true, sorry. Tautology is always true. So in this column, it always shows it's always true, then it's a tautology. And because this one is always false, it's a contradiction because it is a contradiction of the tautology. And you can see it is because it's obvious by the top part of the compound propositions. And then this side, you can technically say it's contingency, but only for a certain case, if it's either true or false. So for conditional proposition, if P then Q, it does the if P then Q or P implies, which is what you would see in a law class or criminal justice class, where if P implies this, then Q does this, where P is a hypothesis antecedent and Q is a conclusion or consequent. If P then Q is always true in most cases, except when P is T and Q is false. Examples are, if an airplane arrived in Europe, then Paris is in France. That's true. T, which is for the P, and Q is T. If Paris is in France, then an airplane arrived in Europe. So if Paris is in France, then an airplane arrived in Europe. False and true. If an airplane is not in Europe, then Botaga is in Spain. False, false. So it's not. I think this is a typo. Not in France. Yeah, this makes sense. If an airplane is not in Europe, then Botaga is in Spain. False, false. There is a tricky scenario for this though. For if then and P. If then it would be if an airplane arrived in Europe, then Botaga is in Spain is true, false. This is strange because it's usually true when P is false, but it would make sense for statements like if Z is a multiple of 9, then Z is a multiple of 3, which is true. But if Z equals 5, it becomes 5. If 5 is a multiple of 9, then 5 is a multiple of 3. For biconditional propositions, you will see if and only P by the definition at the top, and only if Q. P if and only if Q. This conclusion is T when P and Q have the same truth values, like they are both T or both false. This conclusion is F when P and Q do not have the same truth values, like one have T or F, TF, and FT, and not TTFF. So biconditionals only happen when these are happening, but not both of them like this. Now, some problems may have cases like this. When there's a proof or truth tables, you can make a statement and find the logical equivalence by proving it in the tables. Logical equivalence is when two compound propositions have the same truth values, conclusions, even though their constituent propositions are different. So if P then Q, is it equivalent, logically equivalent to not P or Q? Tautology example using logical equivalence, both P and Q are logically equivalent when P if only P and if Q. P if only if Q is a tautology. Prove that this table below are logically equivalent to the equation, which is the equation here that they'll give it to you right here. You are asked to prove it. And then when you prove it, it will definitely spread it out like this. And then when you spread it out using truth tables, you then look at the columns between the two, and you'll see, is it actually true? Like this column here doesn't match this column and this column. For this case, both of these columns do match each other, TT, FF, FF, TT. So then you would just conclude with the logical equivalences written in mathematical notation. And it would be something like this below. Another example, which is not really from the textbook, you might see this possibly on a problem, homework, or exam. You would create a truth table to determine if the two propositions are logically equivalent or not P or not parentheses if R then Q, and if P then parentheses not Q and R. So notice these are 3 variables, not 2 anymore. But because there are 3 variables, the table will be much, much larger, and you will have a different set of combinations now for the true and falses. So first, you'll create the empty base of the truth table. So in this case, P, Q, R, 3 variables, create these true, 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 false, 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 true, true, false, false, true, true, false, false, or Q. And then for R is true, false, true, false, true, false, true, false. So you see that this is the combinations for these 3 variables, different possible combinations. And then after that, you will do the comparison for each to see if the 2 columns here that were asked at the beginning for the equation are logically equivalent or not. So you will fill out the truth table in the sections and then conclude. So it will look something like this. You would do the same method as I taught you earlier. And then after that, you will do the conclusion. Notice that the parentheses are there. That means you will conclude the parentheses first, and then after that, compare it to the second part. So notice right here, see R and Q. R and Q is right here true. So what is not of the true area? It would be false. So that's how it goes. So it's kind of like PEMDAS a little bit, your mathematical, where the parentheses are first, obviously, and then you would conclude it. So this would be the mathematical notation for it. So you would know about these mathematical notations throughout this entire section, and it will be also used in most mathematical notations for calculus or linear algebra and discrete structures, especially if you're proving something using a proof. And it will say this. Therefore, these 2 equations based on these columns, if compared, they are very identical to each other, are logically equivalent, and you have completed the proof. Other times it has cases with converse, inverse, and contrapositive. So a converse is a conditional proposition where if P then Q is, this will turn the converse is if Q then P. If P implies Q, then Q implies P is the converse. Another would be if and only P, then Q. If P, then only if Q, then the converse would be if P, then Q, and if Q, then P. Inverse. An inverse of a conditional proposition is if, let's say, for example, the original is if P, then Q, then the inverse conditional proposition would be if not P, then not Q. Statement would be a shorter version of this. If P implies Q, then not P implies not Q is the inverse. Contrapositive, a contrapositive of a conditional proposition for this original example of if P, then Q is not Q, then not P. The statement to this would be if P, then Q, then not Q, then not P is the contrapositive. Example problem would be consider the original statement. This is what you would see in like a kind of like a homework problem or even an exam. You would see this like consider the original statement. If an intelligence agency detects a credible terrorist threat in the United States, then the Department of Homeland Security issues a national security alert. Write the symbol form of the original statement. So they will give this in blank, but I'm giving the answers because I'm going to explain it over. They will give you this statement, and then they're asking you to turn this statement into a symbol form of the original statement. So since they gave us if and then, we already know right away that this is a compound proposition, which is using if and then. I believe, let me see, and then of a implication. Yeah. Going back down. Since this is an implication, you will write the symbol form, which is if P, then Q, where P stands for an intelligence agency detects a credible terrorist threat, and Q, the Department of Homeland Security issues a national security alert. And then there are parts where they will ask you other questions like write its converse in plain English. So they'll take the original statement. They're asking you to find the converse of this in plain English. So in plain English would be if the Department of Homeland Security issues a national security alert, then an intelligence agency detected a credible terrorist threat. So in order to understand this, you have to understand the definitions, which is proven at the top here. I've given you, and you can technically write this as an equation, part of your equation sheet, and then you would fill in the blanks. So I'm going to read it over. And then write its converse in symbol form. The converse of it is if Q, then P. Because the original is if P, then Q, then the converse must be if Q, then P. And then they'll ask you again the inverse in plain English. If an intelligence agency does not detect a credible terrorist threat, then the Department of Homeland Security does not issue a national security alert. The inverse would be not P. If not P, then not Q. Right? It's contrapositive in plain English. If the Department of Homeland Security does not issue a national security alert, then an intelligence agency did not detect a credible terrorist threat. The symbol form would be if not Q, then not P. Other times on the homework or problem exams, you might see this type of problem, the second version of it, where they'll do the reverse. They'll give you, they'll tell you what P and Q are, and they'll ask you how to write it in symbol form. So notice this one, they gave you this whole statement sentence, or what it is. This time they're giving you P and Q in symbol notation. They're asking you to write in symbol. So I find problem 2 kind of more straightforward compared to problem 1. And if you see, let's go over. By definition, let P and Q be propositions where P, an intelligence agency, detects a credible terrorist threat in the United States. The Department of Homeland Security, which is Q, issues a national security alert. Write the following proposition in symbol form with P and Q and logical connectives, including negations. If an intelligence agency detects a credible terrorist threat, then the Department of Homeland Security issues a national security alert. That is if P, then Q. If the Department of Homeland Security does not issue a national security alert, then no intelligence agency detected a credible terrorist threat. Not Q, then not P. If not Q, then not P. The Department of Homeland Security issues a national security alert only if an intelligence agency detects a credible terrorist threat. If Q, then if P. No, if Q, then P. It is not true, which is false. It is false that if an intelligence agency detects a credible terrorist threat, then the Department of Homeland Security issues a national security alert. This will be representative with not parentheses, if P, then Q, or you can write this in an alternative way, if P and not Q. An intelligence agency detects a credible terrorist threat and the Department of Homeland Security does not issue a national security alert. This will be representative by if P and not Q. Other times you may encounter during this type would be the generic mathematics symbol that we saw earlier for the proof. These are the symbols that you will see also in other proving of mathematical concepts. You'll see this often in linear algebra or discrete mathematics. Not discrete. This linear algebra, discrete mathematics, and differential equations, because there is a lot of proving. They'll give you a proof basically, and you're going to prove the steps, and these symbols are going to help you make the proof easier. Because imagine writing the proof all in words. I feel like that would be taking too long, and it's kind of hard to memorize as well. So most of the mathematical notations for proving, they will technically use these symbols or these generic symbols. So this symbol represents for all, and this backwards E represents there exists. The arrow implies if then. This arrow means and. Upside down arrow means or. Negation means not. And the three dots are in a triangle. Looks like a bowling ball kind of. It means therefore. So examples are predicate a proposition with the variable in it. So these are the types that you'll see in it. These types are predicate, counterexample, quantifier, free variable, bound variable, inference, proof, theorem, proposition, argument, fallacy, invalid argument, axiom or postulate, lemma, corollary, conjecture without the loss of generality. So notice these vocabularies are often used in discrete mathematics, but these ones are also, I noticed these vocabularies are correlated to also law and criminal justice fields if you're using this discrete mathematics of logic and proofs to help you out in those subsections. So a predicate is a proposition but with a variable in it. An example in computer science is PX, user X logged into the system. A counterexample is an example in a domain that refutes a universal quantifier. Example in law that you'll see is a claim for all X. If X is arrested, then X is guilty. Counterexample, an innocent person is arrested, so the claim is false. Quantifier is a generalization that turns a predicate back into a proposition as a variable has a definite list of values. Example in computer science is for all X, if X is a password, then length is greater than or equal to 8. There exists X, user X has admin access. Free variable is a variable in a predicate not bound by a quantifier. Example in computer science would be PX, user X has admin access. X is free. A bound variable is a variable that is a quantifier applies to. Example in computer science, there exists X, user X has admin access, X is bound. Inference is making new statements from old ones. Example in law that you'll see or criminal justice, if one, this is number one, basically. These are statements before you conclude. So 1 and 2 are statements, and then the conclusions are below. That's what the definition of a inference is. If someone commits theft, then they broke the law. 2, the second statement is the suspect committed theft. Because of these two statements, thus or therefore, the suspect broke the law. A proof is a valid argument. An example in CS you'll see is proving that a sorting algorithm always produces an ordered list. A theorem is a well-known proof. An example in CS is that you will see this in binary search works only if the list is sorted. A proposition is a less important proof, which is what you see that we explained in the statements and logic proofs earlier before this. There exists X, a file in the system is larger than 1 gigabyte. Argument, propositions resulting in a conclusion. An example is law. You'll see this quite often in law or criminal justice. If evidence proves guilt, then conviction. And number 2 statement would be evidence proves guilt. Therefore, there is a conviction. Fallacy. A fallacy is an argument where the conclusion cannot be drawn due to logical errors. So you'll see this also in law or criminal justice. If a suspect committed a crime, then fingerprints are present. Also, we know the statement that the fingerprints are present. Therefore, the suspect committed the crime. Invalid argument. An argument where the conclusion cannot be drawn due to the falsity of premises. Example in law, if someone commits murder, then you go to prison. In person is in prison. The person committed murder. Axiom, which is also postulate, a statement seemed to be or assumed to be true, which is in CS you'll see often a program execute instructions sequentially unless control flow changes. A lemma is used in computer science, which is a small proof using a big proof. If a list is sorted, binary search can eliminate half the elements each step, which is true if you were to learn more about binary search and list sorting. A corollary, a theorem that is based completely on another theorem. An example in computer science, you'll see the theorem as binary search requires a sorted list. Corollary is if a list is not sorted, then binary search may fail. Conjectures. You'll see this quite often in computer science as well in software engineering and software dev. A seemingly true statement without proof. Examples are the time complexity. You'll see often efficient comparisons-based sorting algorithms requires at least O and log n time in worst case. So remember time complexities if you're in computer science. So you don't have to learn this, but these are for the computer science people. You guys learn about the big O and the charts with all the time complexities, which is a huge major factor in software engineering and software development, which is why you'll see often they'll test you on leak codes or hacker rank because of this. They not only want you to write the code, they also want you to find the most efficient code per each scenario. Without the loss of generality, which is abbreviated by BLOG, proving two interchangeable variables just by proving once. So you can see this in computer science where for two areas or two arrays, values A and B, vlog assumed A is less than B. Now that we have covered the vocabulary for all of these, and we can see in an example problem that's maybe happening in your homework or exam, they'll give you the signing of the mathematical terms. Let T Y, Y is an IT computer cybersecurity course. DX is Y is the computer science course. GX is X is the government employee. FX is X is the full-time employee. S of X and X, employee X is taking course Y. Now that they give you this, they're going to ask you, okay, now write the symbol form statement using predicates and quantifiers. Assume X represents employees and Y represent courses. So they'll give you every full-time employee, every full-time government employee is taking an IT cybersecurity course. So now that we know what each stands for, we just need to convert it to symbol notation. For every X, there exists Y, and then parentheses, we're going to write the propositional, statements using the combinations of it. If GX and FX, then TY and S of TX and Y. And then for this one will be every employee is taking at least one course. For every X, there exists Y, S of X and Y. There is a full-time employee who is not taking any computer science course. You would write this in symbol notation as there exists X for every Y, and then this giant parentheses comparison is FX and parentheses CY. If CY, then not X. No, if CY, then not S X of Y. And it makes sense because if you reconvert this back, you take this symbol form statement and you convert it back to the original statement, it is true. So that's all they're asking. They're just asking you, I'm giving you a plain English statement of this, and I gave you all what each represents by initializing or signing these variables. I want you to change that to symbol notation while using the mathematical, generic mathematical notations and vocabulary that we have learned previously, which is here, notation symbols. The second part they'll ask you is write in plain English. They'll give you the symbols, and then now they're asking you to take that symbols and convert it into the plain English format based on these variables given. And I'm just going to read it over because it just sounds obvious. It's just asking to convert it. For every employee X, if X is a government employee, then there exists a course Y that X is taking, and Y is either an IT cybersecurity course or a computer science course. There is no employee X that for every course Y, if X is taking Y, then Y is an IT cybersecurity course. Another alternative of this for this symbol notation above here, there is at least one employee taking a course that is not IT or cybersecurity. For this one, part C, there exists an employee X such that for every course Y, if Y is a computer science course and X is taking Y, then X is a full-time employee. This one would be for every course Y, there exists an employee such that if Y is an IT security course, then X is taking Y and X is a government employee. This one would be, it is not true that for every employee X, there exists a course Y such that if X is a government employee and X is taking Y, then X is full-time. Or alternative would be at least one government employee is taking a course without being full-time. So notice that these symbols are quite long, but they're basically just asking you to convert it back and forth. Do you understand the vocabularies and do you understand the symbol notations for math? Basically testing you. And do you understand the propositions that you're doing based on the predicates and quantifiers? So after you know all this, they will give you a section about proofs with logic. So we know this talented person will appear multiple times in logic and proofs, and he will also appear I think, in linear algebra when you do proving, I believe. I'm not sure. I do remember taking the class. His name is Augustus de Morgan, which is in the 1800s. He's a mathematical logic by providing a first rigorous proof using propositional calculus, moving logic from purely philosophical discourse into a mathematical framework. After this guy, you'll see George Boole incorporate these laws into Boolean algebra, which is what you'll see also in linear algebra. They will kind of teach you this too, slightly. And then if you take a Boolean algebra course, it is there. The formal proof was later extended to set theory using element-wise containment, proving that each side is a subset of other, which remains in standard pedagogical proof in discrete mathematics today, which is set theory. You'll see that often in a lot of probability and statistics classes. So you'll see this in your math class, kind of. And you might see this maybe in law and criminal justice, but not in a sense where they're comparing math in the set theory. It's just sometimes they might use this to sort out the evidences and proofs to prove someone is committed something or broke the law. But not really in mathematical terms. They're probably going to write it out in plain English. So why is this important? Because De Morgan's law transitioned from medieval verbal logic to 19th century formal proofs, ultimately becoming the foundation for Boolean algebra. It is critical for simplifying algorithms in CS, interpreting legal requirements in law or criminal justice, and defining set relationship in mathematics and physics. So his law, De Morgan's law, state that the complement of the union of two sets is the intersection of their complements, and the complement of the intersection is the union of their complements. In computer science, De Morgan's laws are essential for circuit minimization and code optimization. They allow programmers to simplify complex, if-else conditional logic and enable hardware engineers to replace expensive logic gates like AND or OR with universal gates like AND or negation OR, basically, with the N, reducing physical footprint and power consumption. Meanwhile, for law and criminal justice, you'll see this in legal reasoning. Criminal justice, these laws govern the interpretation of statutes and evidences. For instance, if a law requires intent and action for a conviction, De Morgan's law or logic dictates that a not guilty verdict is reached if there is no intent or no action. This ensures precise logical consistency when evaluating burdens of proof and exclusionary rules. Meanwhile, in mathematics and physics, you'll see how it's shown in pure mathematics, where the laws are fundamental to set theory and topology, used to define open and closed sets. In physics, particularly in quantum mechanics and digital electronics, you'll see this in your general physics 2 and 3, I think. 3 covers more quantum and more modern physics, and 2 is more circuitry. You'll see that they are used to model state transition or probability, ensuring the negation of complex systems remains mathematically tractable. This also kind of correlates to more advanced physics later on too, based on those branches too. So now that we know these are going to be our proofs. And how we're going to define proofs is that we're going to use our rules, logic, and proof by other conditions. So we're going to break this down to categories. There are 3 categories: rules of inference, inference with quantifiers, and proof methods. So let's go over one by one. So this section, I'm going to go over all the rules of inference and the symbol form and the plain English. So the first part of the rules of inference would be modus ponens. Symbolic form is written like this. If P is true and P implies Q, then Q. Modus tollens is symbolized like this. If Q is false and P implies Q, then P is false. Hypothetical syllogism is represented by this. If P implies Q and Q implies R, then P implies R. That's what you see when 3 variables quite often. They might use this type of rules of inference. Disjunction syllogism would be represented by this. If P or Q is true and it's not P, then it's Q. Addition, you'll see something like this symbol. If P is true, then P or Q is true. Simplification will be represented like this. If P and Q are true, then P is Q. Conjunction would be represented like this. If P is true and Q is true, then P and Q are true. Resolution would be like this. If P or Q is true and not P or R is true, then Q or R must be true. So I know this looks very long and tedious, but they will give you this on the exam. They're going to ask you to memorize these type of rules. And if anything, you don't really have to memorize, like, all of it. If your professor or teacher is nice on the exam, they might give you a cheat sheet where you can add this to your equation sheet, and then you just need to memorize it. If I were you, since the equation sheets are usually 8.5 by 11, like 1 page only, not front and back, it's better to keep and understand the symbolic form, and then you just comprehend what it is in plain English. Yeah, so just to save space at least. Okay, the second part will be covering inference with quantifiers. Okay. For the first part, there exists universal instantiation, sorry. It will be represented by this, using also the mathematical notations where for every x, if all values of P of x are true, an arbitrary value C also satisfies P of x. Universal generalization is this represented this. If an arbitrary value C is satisfied P of x, then P of x is true for all x. Existential, instantational, I hope I said that right. Existential, instantational. Yeah, these kind of complex, but yeah. This states for every x, P of x, if then PC. If there exists an x satisfying Px, call that value C. So for the inference with quantifiers, it is crucial to also add the mathematical notation of for every and there exists, because that is what it is that you need to put. Meanwhile, above, when you go to the rules of inferences, they're not really doing that. They're doing propositions. So combinations of propositions with quantifiers and predict dates. Exist until generalization. If C satisfies Px and some x satisfy Px, And then the third part would be proof of methods. So this is what you would use for proving. You might use this for proofs too. Direct proof. Prove a statement by assuming the premises are true and deriving the conclusion. Proof by contraposition. It states that assume the negation of the conclusion, then prove the negation of the premise. Proof by contradiction. Statement of the symbol that we just shown previously. Assume the negation of the conclusion, derive the contradiction, conclude the statement is true. Proof by exhaustion means prove a statement by checking all possible elements of the domain. Proof by cases, split the domain into cases and prove each separately. Prove by equivalence for statements of these symbols. Prove both directions separately. Proof by chaining, chain multiple conditions, P of X, Q of X, Rx, P of X, like if, then, if, then, if, then. Proof of quantifications for array. For every variable, find counterexamples for there exists, prove existence using previous methods. So for this, you'll see this kind of example, another one, based on all those proving is they'll give you a set in the homework or exam, something like this. By definition in mathematics, let this be this. I'm just basically using the previous example from the problem, and I'm doing this into the proving statement, like proofs. And then after they give you the set of the domain and these variables, they tell you what each variable is assigned and what it is. Fill out the steps. They're going to ask you, they're going to give you a table in the exam, and they're going to ask you, since I gave you all the variables and what they mean, now fill out the table by the steps, symbolic expressions of rule to expressions or statements, then make a conclusion and state the rules of inference or what method you proved it. So the first part A, we're doing inference with quantifiers. Premises 1, plain English, all government employees must take a cybersecurity course. Alice is a government employee. That's what they give you, right? So now you're going to prove it. You can do the steps, symbolic expression, rule. You're going to write the table. If anything in the exam, they're going to give you a blank table and then with just steps numbers. And then you just fill out the rest of these. Okay? So it's kind of long, but that's just how it is. And most of these proofs are not really meant to be lengthy or long. They're meant to be showing you, do you comprehend how to write a proof and understand the rules based on those proofs. So they're going to give you a symbolic expression of what you're asked to do. Convert this to symbolic. And then it says rule, premises. Convert this to problem, universal instantiation by for all elimination. You're going to put the symbolic expression, and then you're going to say modus ponens. And then thus the conclusion, Alice is taking cybersecurity course. And then the rules that you use, they'll ask are these ones. Okay, and then this will be the second premises. I'm just gonna pause it. You guys can look at it. And then rules of inference. And then these are proof methods. They're gonna use these ones. If an employee is a government employee, then they must take a cybersecurity course. See how the steps in reasoning rule, and then direct proof conclusion. Every government employee must take a cybersecurity course. So this one's combination of all of them. And this one's just the previous one that we just explained, the first part, rules of inference. So they're going to ask you, this part is the rules of inference with quantifiers proof. This one's the proof methods with everything in it, including inference. And the mathematical notation of there exists and for every. So there you go. And then this is the statement 2. And then what you just learned from these proofs using the concept learned, they're going to give you another long proof. Maybe if your professor is kind of mean, they're going to give you like proof by contradiction problem. Prove that all 4 integers n is greater than 0. If n is not a perfect square, then square root n is not an integer. They're not going to give you the context, but I'm explaining to you why this is important for computer science. Ensures algorithms are perfect squares, like data sets, and it is not, do not assume these type of assumptions. So this proof, which is just these 2 bullet points, they're going to ask you, they're going to give you this proof in this problem, and then they're not going to give you anything else. They're going to ask you, okay, prove it all using what you just learned right now. So the steps to break it down is that you're going to define the logical symbols. You're going to write this down, P, Q, write each of them, separate each 2, write the original statement. And then for step 1, you're going to assume the negation, proof by contradiction. Negate the statement, use implication equivalence using this equation. And then you're going to apply what we learned with the guy. to Morgan's law. Why? Because that is part of one of the laws to help you prove it, interpretation about it, and then identify the contradiction. And then after that, you're going to write the conclusion after you prove it. So since assuming the negation leads to contradiction, this is true. If n is not a perfect square, its square root cannot be an integer. So a compact answer will be shown like this. You'll see this, what you will see at the exam. They won't give you this rules here, but that's what you would write usually when you first see the problem. So they'll give you the problem question and you're going to say, okay, what rules do I think is in here? Okay, I'm going to list them all. And then after I list them all, you're going to say, okay, let's break down this problem, right? Here's the problem converted to the symbol form. And then we're going to break it down to the official notation. And then we're going to break down to each step. So this is step 1, this is step 2, this is step 3, this is step 4, and then this is step 5. Therefore, not P. If not P, then not Q. Okay, this is crucial to understand the proof. And the proof, they don't want you to write it all in English. They want you to write it like this. I just made it more, break it down for you so you can see it. So I'm going to go back up. I'm going to slow it down. Pause the video if you want to go over the proof by yourself. It's quite long. Okay. And that is how you will prove during the exam or homework assignments about these laws that we all learn and how it applies to these logic and proofs. So they're going to give you logic and proofs. They're going to give you a bunch of logics using propositions and some mathematical notations using variables like this. And they're going to ask you to use all these rules that you learned so far and write it into a proof standard as you prove it. So how is this important? Because all of these are mostly used in computer science, mathematics, physics, but it also used in law and criminal justice too, because if you notice in these proofs, you can technically convert these if you were to write it all in word by word, and it would make kind of logically sense if you were to use it in law or criminal justice. So that's why I'm going over this section and how it relates to it. So there it is for the logic and proofs, and I hope this is very useful. If you would like me to make more videos about mathematics, IT, physics, computer science, cybersecurity, or even law, legal studies, or criminal justice, feel free to let me know. Otherwise, I will keep uploading more educational videos for my channel to help make this useful for everyone. Thank you for watching.